Today we will go through all the questions in weekly problem set 7. So let's begin. For the first question, we define a function fa equals to fax equals to a times x mod n. And the domain is from 0 to n minus 1. And the range is also from 0 to minus 1, of course. And when is this function a permutation? Only when the function is 1 to 1, right? And as the size is the same. So 1 to 1 and so which means this function should be bijective. So let's consider if the greatest common divisor of a and n is not equals to 1. Let's change the color. Then which means the least common multiplier of a and n should be k times a, and k is smaller than n. Because the multiplier of these two is k times a, is n times a. So these two are equivalent. So what can we know? We can know that fa k equals to fa 0 equals to 0. Because k times a is the multiplier of n, so this mod n must be equal to 0. So as this is true, then this function cannot be a bijective function, which means this is not a permutation. Then what if the greatest common divisor equals to 1? Then we can create another function called fa inverse, where a power negative 1 times a equals to 1 in mod n. And what's the relation between this function and this function? Basically, fa negative 1 fa for some x equals to x, right? Why? Because this one equals to ax mod n, and then a negative 1 mod n, which equals to a times a negative 1 times x mod n equals to x mod n. And as both the domain and range is smaller than n, so this one is just equals to x. This means this one is the inverse function of fa. And if this function have an inverse function, then this must be bijective, right? So we know that only when GCDA equals to 1, it is a permutation. Then what's a circle in a permutation? Let's consider when n equals to 5 and a equals to 1. The domain and range is 0 to 4. When a equals to 1 and when x equals to 0 to 4, they just output 0 to 4, right? Because 1 times what is itself. How many circles for this one have? We have 0 to 0. We have 1 to 1. And 2, 2, 3, 3, 5, 5. Each of this one is a circle itself, right? So we have 5 circles here. And when a equals to 2, we have the following results. Then what happens there? Similarly, 0 is still a circle with 0. But for now, here 1 we went to 2, and 1 went to 2, and here then we go to 2, 2 went to 4, and we go to 4, 4 went to 3, right? And we go to 3, 3 went to 1. So for now, we have 2 circles here. We only have 2 circles here. But why it happened? How we get the number of circle? So let's say except the first circle must be 0 to 0 itself. For the next circle, we begin to 1, And then what we will got? We will got FA1. And the next number is FA1. And go on. So what's this one? This one is A times 1 mod A. This one is A squared times 1. And then next is A power 3 mod 1 and go on. So what's the length of the circle? This is A power 0, of course. When it becomes a circle is when we found some A power k equals to 1 mod n. So which means for now we will create a circle with length k. Yes. So this k will cause the order of A mod n. And if we found the k, then we've got that every circle of length is also k. So the number of circles we have is a minus 1 over k. And of course, the plus 1, which is the circle of 0 itself. So finally, we got the number of the circles is just given by this slide. Okay, this question is done. And for question 2 and 3, they are discussed in the lecture. So let's directly go to lecture 4. Okay. Oh, sorry, the question 4. How many numbers can be between 1 to 50 in the set, and there's no two numbers sum can be a multiple of 7? We know that if we want to divide everything inside this set with 7, we can divide them based on the remainder when they divide by 7. And there are 7 possible cases, which is from 0 to 6. So how many cases divided by 7 is with mod 0? 7, right? Because 50 equals to 7. So we know 7, 14, and blah, 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 to 49 are this one. And how many of them mod 7 is 1? It's 8, right? Because we have 1, then 15, and 15. We have 1 more. But we mod 2, we only have 7. And 3, 7, 4, 7, all the others are 7. And then you will find another interesting thing. If we contains any one which divided by 7 modulo is 1, we cannot include any number which the remainder is 6, because some of them the remainder will be 1 plus 6 equals to 7, which is 0. Then this means this is the multiplier of 7. Just like if we know that x can be divided by 7, the remainder just means the remainder is 0. So only one set of these two can be included, similarly to 2 and 6 and 3 and 4. And we know that 1 has one more element, so 1 must be included, and 6 is not. And for the other two pair, just randomly choose 2. No difference there. So we know that it's 8 plus 7 plus 7. But remember, can we include anything with this? We can only include 1, right? Just one element from this. Because if we include 1 of this and sum with any other thing which is not a multiplier of 7, then it's okay. But if we include 2, the sum of them must be the multiplier of 7. So we can only add 1 again. And this is the final answer. Okay, cool. Okay, let's go to next question then. For the question 5, we'll have following two sequences, which is x and y. And we want to show that except 1, no other terms will appear real in both of the sequences. So let's see. So basically what can we do is we can calculate all the values mod 8. And we'll find something interesting thing. What happened when we mod 8? We got 1, 1, 3, 5. And that is what value? It's 3 again, and it's 5 again. And that's why, suppose for the next value, it should be, its mod 8 should be 3 plus 5 times 2 equals to 5, right? Or equals to 3, so. Oh, sorry, this is 5 plus 3 times 2 for the next one, because the xn is 5 and xn minus 1 mod 8 is 3. So which equals to 11 and, oh, sorry, and 8 mod 8 equals to 3. So next one is also 3, and if we do next one, then 3 plus 10 mod 8 equals to 5. And next one must be 5. So it will go on like this. And for y, what will happen? It will be 1, 7, and this is 1, because 8 times 2 is 16, and then 7, and then 1 and 7. And why? Because consider the next one. It is 2 times 7 plus 1, but plus 1 times 3. So equals to 17. So next one is 1. And the next one will be 2 times 1 plus 7 times 3 equals 21 plus 2 equals 23. So, which is 7. So it will keep going 1717, and the above one will keep going 3535. So no one will can mod 8 and equals to both two remainders. So this shows that no term will appear real in both sequence X and sequence Y. Okay. Okay, for this question, 1 to 14 consecutive numbers, and each of them will be a multiplier of prime number between 3 to 11, or 2 to 11. But we know that among the 14 numbers, there are 7 numbers are even, which is a multiplier of 2. So we can simply ignore them, only consider the 7 odd numbers. The 7 odd numbers are 1. Let's consider the first, second, third, 4, 5, 6, 7. How many of them is multiplier of 3? 2 or 3, right? Because it can be either 1, 4, 7, or 2, 5, or 3, 6. How many of them are multiplier of 5? 1 or 2, right? And 1, 7, 1, 11. So let's consider each prime is a pigeon and each number is a whole. We have 3 plus 2 plus 1 plus 1. So we have 7 pigeons and we have 7 holes. So we want exactly 1 pigeon in 1 hole, then this sequence will satisfy our requirement. Then as the 3 pigeon for 3 can only put in these 3 holes, so that failed. And then for the 5, how can we put that? We found that there's no way to put them, right? Because they can either put in 2 and 7, or 1 and 4. But if we put 2 and 7, there are 2 pigeons in 7, and we don't want that. Similarly, it's for 1 and 4, it's the same force. So this one is wrong. We cannot do this. And then let's try to do the second part. We have 1, 2, we want 21 And among them, we can make 11 of them as even number. So we only need to consider, sorry. So we only need to consider the left 10 numbers, 1, 2, 3, 4, 5, 6, 7, 9, 10. And for now, we have 5 possible parameters to take. Then similarly, let's check how many multiplier of each numbers can have. 3 is 3 or 4, 5 is 2, 7 is 1 or 2, 11, 1, 13, 1. So how many pigeons we have? 4 plus 2 plus 2 plus 1 plus 5. Exactly 10 pigeons. How many holes we have? Also 10, right? Let's try the same thing. First, we put the 4 pigeon with number 3. Then 1, then 4, then 7. So, wait. Oops. Oh, what happened there? We forgot 8 here, so okay. And then we try to put the 5 here. We can put it in 3 and 8, right? And then we want to put the 2 7 pigeons. We can put it in 2 and 9, right? And then left 1 to 11, 1 to 13. Seems is okay. And then we got that this seems okay. And then we can try to find something, just real program maybe. And it's easy to find that this one is satisfy our requirement. Okay, next question. We have 85 digits here, but if we want to write program to go through all of them, we are wrong. 10 power 85 numbers in the loop because we have these possible cases. That's impossible, right? So let's try to remove some not possible cases. Let's consider what's the maximum of the 85 digits of it's at most this one, right? But if we have 10 digits more than 1, then 2 power 10, at least 1024 is already larger than the sum of digits. So we know that there are at most 9 digits is larger than 1. And let's consider if we want to make the number as larger as possible. So the order of digits will not influence the sum of them and the multiply of them. So we will order the digits like a decreasing order. And of course, there is no zero in it. So the case will looks like something like 987 blah blah blah, and then in the first one and 1111 blah blah blah. Now we know that for now there are already at least 75 ones. So for now it's already okay to use program to get the answer. But if you don't want to do that, here we can do the following thing. There is also some way to directly get the things. So consider, as we know that there are already 76 ones. Already 76 ones. So currently what's the maximum number of sum? 76 ones and 9 digits at most 9, so which equals to 157. It's smaller than 2 power 8. So then we know that we can add another 1 here. Okay, interesting. Then let's consider, if we want to go on, can the first digit be 9? Let's ask this question. Suppose the first digit be 9. What can the multiply be? We have 19, we have 99, we have 108. What else we have? We have 126 and 1355. 135. But is this one possible? This equals to 9 times 11, right? Do we have a digit called 11? No. All the prime factor of it should be less than 10 because it's the multiplier of all the digits. So this one is not possible. So similarly, that's why we identified 117. This one is removed because of the same reason. So only these 4 possible cases, right? And then with this case, we can directly get the answer. So 90, then we got the 952, right? And then 1, 1, 1, 1, 1. And we check the sum is not the same, so wrong. For 108, it's equal to 9. 108 is 943, right? Because it's 9 times 4 times 3. So 943 and 1, 1, 1, 1, 1. And we check sum is still not true. And for similarly, we check 126 and 135. All these calculations are really easy, and you can find that both of them are not true. And by the same way, you can also check 8. Can A1 be 8? And the answer is this. And the right answer is 3, 2, 2, and 1, 1, 1. Here is how you get this by hand, but if you want, from this step, you can begin to use programming to get the answer. So next question, we want to find the inverse of it, of A and A. Okay, one quick question. If we know GCD-AN is equals to 1, and we know that we can write something like this, then that means that AX plus NY equals to 1, mod N, because 1 mod N is 1. And as NY mod N equals to 0 because NY is the multiplier of N. So we know AX equals to 1 mod A, which means A is the inverse of X. So if we can got this X and Y, we can directly, if we got this, directly got this inverse. But how to do that? Then we will introduce the extended Euclid algorithm. According to the basic Euclid algorithm, we know that GCD-AB equals to GCD-B mod A and A, right? And also we know that these two formula. So if we set these two are the same, and we change B mod A, B minus B divided by A times A, and this one is the lower bound. And we run it, we can got this formula. So AX plus BY equals to A times this part, and then B times X1. So we can get something interesting formula like this. And then if we can first got the last one, because we know that GCD maybe 0, 0, A equals to A, and it's equals to 0 times 0 plus A times 1. And then we can go back to got this A and B. Let's try to use a case to show that. Suppose A equals 28 and B equals to 161. And the first time we got remainder is 21 and put 21 here and 28 here. And then we got 7. We put 7 here and 21 here, and then it's 0. So we got the last case, we got the GCD is 7, right? And then x3 equals to 0, y3 equals to 1. Let's go on. What's the formula be like? X equals y1 minus the division plus x1. So here is 1 minus 3 times 0, which is 0, so this is 1. And we put this one to here. Similarly, with the 1 to here, 0 minus 1 times 1 is negative 1. And then -1 to here. 1 minus -1 times 5, which is -5. So 1 minus -5 is 6. So we got this thing. Let's try to check that. It's 7, right? Which is the GCT. So we got this thing. And this one can be easily read as a recursive function. Looks like this. It's really easy, right? Just take these two functions is exactly these two formula we get. And this case is simply the basic Euclid algorithm. So not anything hard. Okay, let's go to the next question. From problem 2, which we jumped off, we know the Fermat-Little theorem, which shows that this case. A power p equals to a mod p when p is a prime. So when p is a prime, what we know? We know that a power p over a equals to 1 mod p. And so we owe a over p over a squared times a equals to 1 mod p. Right? What does that mean? It means this one is the inverse of a modular p. So this one equals to a p minus 2. Then this answer is really simple. Just def blah 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 and return which we got a and p. Return a power p minus 2 and maybe mod p. Then we are done. Okay, for next question, if you understand the Chinese remainder theorem, then that would be easy. Let me first remind you these things. Consider we know x equals to 2 mod 3, x equals to 5 mod 4. What is x? How can we solve that? Here is the way we do. We want to separate x into two parts, x1 and x2. And what we want is x1 mod 4 equals to 0. And so let's write here, want x1 mod 4 equals to 0. x1 mod 3 equals to 2. And similarly, want x2 mod 3 equals to 0. x2 mod 4 equals to 5. Then the sum of them can satisfy both of the formula, right? But how can we do that? One easy way to do this is to make this, we want x1 be the multiplier of 4. Then its mod 4 must be 0. And then if we times 4 inverse, mod 3, this is mod 3. And then times 2. It mod 3, the module of it mod 3 will be 1 times 2 equals to 2. So similarly, x2 can be 3 times 3 inverse times 5. And if we do so, x1 plus x2 equals to x will satisfy both of the requirement. Okay, so that is how we do basically. We want God, suppose for now we have two number 0 equals to remain 0. Let's write something like this. Let's suppose something like this. We have so many k equals to k. We have k equations supposed in this formula, and all the num are relatively prime to each other. So firstly, what's the multiplier of all these things? We just go, because we are writing program, so we can simply write m equals to the multiplier of c 0 k equals to 0 to k. Simply write a loop to do this. M is the product of all these things. And then For each time we get the result equals to m divided by the sum of the num I and times divided by num I and inverse and then times rem I. This is just creates the xi. And by get sum of them, we will got the result. This one is easy to write into the code things. You can check the code version in the PDF version of the algorithm. Okay, so basically that's all for today's tutorial.